happy that we're just 10 people because this is the first time I've done this, and I'm going to need you guys to stop me when it gets confusing, difficult, right? We have 3 hours, but I have like about 5 hours of material to get through, okay? So there's going to be a lot of concepts in this, okay? And if you miss something, then you could very well spend the rest of it confused, okay? So stop me, get me to clarify something if it doesn't make sense, okay? Other than that, you know, it's going to be concepts, a bunch of notation, which is going to be unfamiliar, probably, unless you're... First of all, does anybody here have a background in physics or quantum mechanics? No, this is what I expected, all right? So I'm going to show you the notation, right, that is used in physics, which is different to that which is used in mathematics or engineering or high school. And it's important to kind of get used to that notation because that is the notation which is used throughout quantum. Okay, if you go to Qiskit website or if you go to anything about quantum information, that is the notation which is used. So there's going to be a lot. You guys are going to have to pay attention for 3 hours. I understand this is going to be hard. We're going to take breaks, all right? And I am not going to be thrown off my game if you guys talk to me, tell me things, ask me questions, all right? So why are we going to do this? So first of all, quantum information is, in some sense, the easiest way to learn quantum mechanics, right? You are working with a finite dimensional Hilbert space, a finite dimensional vector space. You are working with finite matrices, finite vectors, no integrals. It has applications in quantum computing, quantum communications, stuff which doesn't exist today. Well, it exists, but in labs. But we're going to see what happens over the next 10 years. IBM are currently scaling up their quantum computers. It is essential for understanding entanglement and the theory of open quantum systems. Open quantum systems again has applications in quantum computing. It's essential for that. And it also is essential for understanding quantum foundations, right? Foundations are questions like, the measurement problem. What's going on with, cats, murdered by decaying radioactive elements. And we're going to start, so for this first hour, I'm not going to talk about quantum at all. I'm going to talk about classical information, classical probability, and I'm going to introduce a bunch of notation, okay? So this is going to be boring maybe, right? But it's also essential, okay? And it's essential for the reason that it's going to give you a point of comparison that once I start writing quantum states, or showing quantum states on the slides, you'll be able to see what is really the fundamental difference between quantum mechanics and classical probability. So we're going to start at considering an experiment with a discrete set of outcomes, okay? Discrete, okay? By discrete, I also mean finite, okay? Working in finite dimensional spaces. So a coin toss, the outcomes are heads or tails. A dice roll, the outcomes are 1 to 6. Arriving at a traffic signal, the outcomes are red, yellow, green, right? A classical probability distribution is a mapping from each element of this space set of outcomes to a number, okay? Which we call a probability. So for a fair coin, we map, heads is mapped to a half, tails is mapped to a half. For our traffic lights, we have something more unbalanced, right? I don't know, I made those numbers up. But now, typically, ordinarily in probability theory, we write that as a function called a probability mass function, or in the continuous case, a probability distribution function, probability density function. But here we're going to do something different, all right? We're going to write probability distributions as vectors. What's the difference here? Well, only that we've labeled the outcomes by an integer, okay? That's all. A vector is a mapping from the integers to something, okay? And immediately we see that there are some constraints on what we can do here, okay? Each probability is a non-negative real number, okay? And they have to sum to 1, okay? Important, okay? Trivial, but important. It's a definition. Now, we're going to do something which might look a bit useless and a bit trivial at first, okay? We're going to say that a vector can be written as a matrix with 1 column, okay? I can do that. That's a vector, right? If you go back and look at the definition of a vector, that's a perfectly legit vector. Or I can write it as a matrix with 1 row, okay? Same deal, no difference. It's still a vector and somehow it's isomorphic, right? But we're going to call these guys row vectors or dual vectors. And we'll see in a second why that's useful. At first, it looks like something completely arbitrary. Now, in physics and in quantum information, these kind of vectors, the column-y ones, we write using this funny notation. We label them, okay? The thing in here is an arbitrary label. I put psi because this doesn't mean much to me. That's like the default thing, like x or foo, right? And if it's a column vector, then we call it a ket, and it has the pointy bit going that direction, to the right. We label row vectors, we call them bras, right? And the pointy bit goes to that way, right? Seems silly. Well, why would we do that? We'll get to that in a second. Now, for vectors of real numbers, you can see that I can get from a ket to a bra by taking the transpose. Trivial, right? I just stick it on its side, okay? So there's a relationship between the bra and the ket. This is going to be different for quantum. Now, in high school, you guys remember about inner products, dot products, okay? In high school, we wrote them with I don't know if a laser pointer here, seems like not. No, let's not press random buttons. So this dotty notation here is how we write an inner product in high school, okay? Now, if you think about it in terms of matrices, you know, if we say, I don't know how you want to write, well, these are column vectors. So we have 1, 2, dot, 3, 4. You know, your rule is you blah, 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 blah. This actually turns out to be the same thing as 1, 2, 3, 4 in matrix multiplication, okay? So we can write this inner product in that form as the transpose of the first vector times the second vector, okay? A bra times a ket, which we just said is the same as that, okay? A bra times a ket, and we usually write it like that. We haven't done anything here, okay? That means exactly the same thing as this here, okay? It means exactly the same thing as the dot. That's all it means, all right? Inner product. It's a number. We're never going to use that notation ever again, and we're never going to see it ever again. You will never see it in quantum. The length of a vector, or the norm, is the square root of that, of the inner product with itself, okay? So that is, remind me what the length of, how I calculate the length of a vector. What's the length of this vector? That squared plus that squared, take the square root, okay? Euclidean norm. Okay, yeah. Well, tell me, what is the length of that vector? That one's a useful one to know. Square root 2, okay? Square root 2 is going to come up over and over again. The only reason 1 over square root 2 comes up and over again is that the length of that vector is square root 2, okay? Okay, so when we want to normalize it, I have to, and make it have length 1, I divide by square root 2. Two vectors are orthogonal, perpendicular, if their inner product is 0, okay? So, are these two vectors orthogonal? I heard yes. Yes, because 1 times 2 plus 1 times negative 2 is 0. So an incredibly fundamental concept in vector spaces, okay, which is in everything, okay? If you're doing Fourier analysis, if you're doing anything in quantum mechanics, we're working with vector spaces, right? And a fundamental concept in the whole, you know, even thinking about vector spaces is this idea of an orthonormal, of a basis, an orthonormal basis in particular, okay? What's an orthonormal basis? It has ortho in it, and it has normal in it, okay? Normal refers to each vector, it's a basis is a set of vectors. Each vector has length 1, and the vectors are all mutually orthogonal, okay? Orthonormal, orthogonal length 1. The size of the set has to be the dimension of the vector space. This is a little bit circular because actually that's the definition of the dimension of the vector space. It's the largest orthonormal basis, orthonormal set of linearly independent vectors that you can make, okay? The point why this is important and why it's important that the size must be the same as the dimension of the vector space is if we take, for example, let's start with an example. If we assign to our heads and tails, probability distribution, we assign these vectors here, 1, 0, 0, 1, is going to be the base of our vector space, right? Remember we said that, we're writing a probability distribution as, a half, okay? Where this is the probability of heads and this is the probability of tails. So the basis vector corresponding to heads is the one with a 1 here, and the basis vector corresponding to tails is the one with the 1 there. Yeah? Is that clear? Okay? And we label the basis vectors with the outcome in this case. Okay? Yes. Yeah, okay, sure. So, we'll get to a formula in a second which makes it a little bit clearer. Here I have a probability, let me take the example, probability distribution of heads and tails, okay? Half, half, okay? This is a two-dimensional vector space because I have two things. The simplest orthonormal basis for this space is the one with 1, 0, 1, 0, and 0, 1, okay? This is an orthonormal basis. Each vector has unit length, okay? 1 squared plus 0 squared, square root. And these vectors are orthogonal, 0 times 1 plus 0 times 1, okay? So this is an orthonormal basis for the space of vectors in which this probability distribution resides, okay? And so I'm going to get in a second to why that's important. Does that make sense? Okay. Also, I'm going to label this guy and this guy like this, okay? I'm just assigning a name to... Yeah, because it's the ket that corresponds to that. Yeah. Okay. So I said, so that's what I was about to say. Check that, calculate HH. HH is 1, as I just did over there, right? So it's length 1. Calculate heads, tails. Heads, tails is 0, so this is an orthonormal basis, you can see. Okay. Now, the important thing about bases is that they let us expand and express any vector in terms of the basis vectors. Well, the one important thing about bases, okay? So this is critical, right? The critical thing here is that we're able to express our probability distribution as a sum over these basis vectors. If anyone didn't understand what I just said, please yell at me now so I can say it again. This is critical. We good? Okay. We can do the same thing with bras, and it looks the same. We just have bras there, okay, instead of cats. Okay, we're not going to write it like this very often. In general, in full generality, we have a formula like this. It says any arbitrary ket can be written as a sum over the basis states. In this case, our basis states or our outcomes are H and T, heads and tails, okay, of some number, okay, labeled by the basis state, H and T, times a basis vector, okay? Our basis vectors were these guys, okay? Heads and tails, okay? I'm going to do something a bit more on that in a second, okay? But look at that formula. Convince yourself that is a generalization of what we just wrote here, okay? To an arbitrary vector space. We also get something really nice that we use all the time in calculations. We can write the inner product between basis vectors in terms of this weird little delta symbol called the Kronecker delta, which says this inner product is 1 when I and j are the same, and 0 when I and j are different. Okay, so if we had h here and t here, they're different, 0. If we have h, 1, t, 1. Okay? I know this seems silly, but it actually turns out to be super nice when you're doing calculations, which we'll see in a second. Okay. Yep. No, fine. I know I'm going fast, yeah. Yeah. No, it's fine, that's fine. I'll slow down also. Yeah, this is the definition of this symbol here. Okay. Yeah, okay. Yeah, I apologize. This is the definition of this symbol, okay? I'm saying that when we're doing calculations, we will very often, in fact, what we want to come out is inner products of basis vectors, okay? Because then we can evaluate them to a number, okay? Or more correctly, to a delta symbol. I'm going to show an example in a sec, right? Okay? So these probabilities, the probability of getting a heads is now an inner product, okay? So let's check this, all right? So we have this probability distribution we had here of a half heads plus a half tails, okay? That was that probability distribution I wrote super messy over here, okay? Now, I'm telling you that the probability of a heads is the inner product between the basis vector heads and the probability distribution itself. I see people staring at me, so let's do it. Right. So let's calculate h psi, okay? This is equal to h half h plus half tails, right? This guy comes in, goes straight past the number, okay? Numbers and vectors commute, okay? You can view that as a property of linearity of the bilinearity of the inner product, or as a property of well, probably that. Anyway, numbers and vectors commute. This guy goes straight through, okay? Sorry, you can't see, but I just realized. Goes straight through. It distributes over, actually. Again, this is, if you want to say, a property of the bilinearity of the inner product. Goes past this, and we get, as soon as this guy hits this guy, now we gotta, this guy's a matrix, it can't keep going, right? It stops there, okay? And we got this. What's this? 1. Over here we have heads, tails, which is 0, okay? This dies, I'm left with a half. Is that the probability of heads? It is, okay? Super trivial, right? All I'm doing is showing you how to manipulate these symbols, okay? It's not, oh shit, how did I get there? Oh, because I'm, damn. Ooh, okay. Yes, okay. So super trivial. We knew this to begin with, okay? Because I defined that element of the probability distribution was the probability of heads, okay? I'm just showing a different way to write this, to write this down, okay? Because we're not going to deal with things as trivial as this in future, okay? All right. Mm-hmm. Capital H is a label, okay? Yeah. When I'm allowed to write anything I damn well please in here, if I want to write, foo bar in there, that's fine. Yeah. All this says here, all this equation here says is that it's the heads element of the probability vector that gives me the probability of heads, okay? It's not saying much, all right? But what I'm saying is that... No, this is a vector. H is a label, ket H is a vector. This is also a kind of vector called a ket, okay? Yeah. Yeah, no, we wouldn't say probability of a vector. No, H, here, this is just the probability of heads, okay? Yeah, I understand. That's why I'm saying the notation's confusing, right? But we'll get it, okay? Okay. In general, we write this like this. The probability of an outcome is the psi I, the coefficient I talked about before in the vector, which is the inner product of the basis vector with the vector, okay? I'm not saying anything deep in here. I'm saying something super trivial, okay? Okay. Let's prove that formula. Again, we kind of did it, but I want to, once again, just show how this is a very common kind of computation we do, right? So, let's calculate I, that's a basis vector, times an arbitrary vector, psi. That is I times, how can we expand it? Does anybody remember? Formula I had up a second ago. Yes. Sorry, there should be a J here since I've used I there, okay? Okay. Everybody fine with that? Okay. Once again, this guy comes in, goes straight past the sum. Linear, okay? Goes straight through the sum, straight past this number. And we're going to get the sum over J of psi I, J. Okay? Does it help? Do I need to write this out in terms of in high school matrices? No, it's okay? Okay, all right. What's this equal to? Delta ij, okay? This is what I am always looking to get, guys. I'm looking for a delta inside a sum over one of its indices. Okay? Because then it says that, well, this is going to be 0 every time j equal to I, and it's going to be 1 when it's going to be 0 when j is not equal to I, and it's going to be 1 when j equals I. So all the terms with I not equal to j fall out, drop out, and I am left with psi j. Okay? This is a kind of computation we do very often in quantum, okay? This is a very, very simple example of it, okay? So what I get is that this coefficient in the expansion of a vector in a basis is just the same thing as the inner product of the basis bra with the vector. Okay? It's nothing incredibly deep, but it's a useful thing. Okay? This is going to be a little bit different in quantum. We can even think about, this is a bit silly, we never do this, but we can even think about computing the average value of some observable quantity, right, in terms of an inner product. So imagine if I had some game where if I flip a heads, I win $1, and if I flip tails, I lose $2. Then I can put those results, those outcomes, in a bra, and then if I multiply it by the probability distribution, there's this cat here, half-half, the same one we've been looking at all the time, then I'll get the expected payoff, the average payoff of playing this game if I play this game a lot of times, right? This is completely different in quantum. It's ridiculously much more complicated, insanely much more complicated, and it's the only reason I'm showing you here what it would be in classical probability theory. Is it an observable, if you like, or a measurement? Is just a bra in classical probability theory. In quantum, this is much more complicated. All right, so how are we going on time? Good, excellent. So let's talk a little bit more about interpreting this stuff. That was pure notation and pure, linear algebra in physics notation, okay? A probability distribution, what does that mean? It represents our knowledge about the outcome of an experiment before we perform the experiment, okay? So a probability distribution, our vector we had, half-half, represents what we know about this coin before we actually flip it, or alternatively, before we observe the result of flipping it. So this is reinterpreting the notion of probability in terms of information. After tossing the coin, after flipping the coin and observing the outcome, what happens to our probability distribution? What's our new probability distribution? It's a result, right? Exactly. It's like H or T, okay? So it has the effect of collapsing the probability distribution into a single basis state. So before we tossed a coin, we could describe our knowledge of the state of this classical system, a coin, as being in a superposition. So times anyone tells you that superpositions are a fundamental feature of quantum mechanics, well, not so much, right? They're a fundamental feature of probabilistic of stochastic systems, in a way, okay? At least from, that perspective of information theory, right, of information. There are differences, obviously. Who here knows what entropy is? One person. Okay, good. I didn't either. A couple of years ago. So the entropy of a probability distribution is a measure of how much information we obtain after performing the experiment and getting a result, okay? Or alternatively, you can think of it as the amount of randomness in a system, okay? To the extent to which this system is random. Or some people say the amount of surprise. But we want to quantify this. Now, what we know about this is that, what should the entropy of heads be? Wow, 0. It's non-random. We know everything there is, okay? So, there's no extra information we gain by revealing to ourselves that, the thing we knew was heads, right? What about a state like this? Well, that should be non-zero when we perform that, even though it's an unfair coin, right? It's more often tails, it's more likely to be tails. When we perform this experiment and we get a heads or we get a tails, we get some information, okay? So this state has a non-zero entropy. Do you think this state has more or less entropy than the one we were working with before of half heads plus half tails? Does this state here, an unfair coin, have more entropy or less entropy than a fair coin, the one we were doing before? Correct, yes. We get less information when we get the result of this experiment, okay? If you think about trying to encode messages in Shannon information theory, if you were trying to encode messages using, you would need more of these unfair coins. So, okay. The next thing we require for entropy is that it should be additive, okay? If I have 2 bytes, if I say that a byte has 8 bits of information in it, how many bits of information does 2 bytes have? 16, right? So entropy is a measure of information. It should be additive. When I put 2 systems together, the entropy of the combined system should be the sum of the individual entropies. Okay? This is where the definition of entropy comes from, nowhere else, right? Even in thermodynamics, it's really just that. So a quantity which satisfies these requirements is the expectation of the negative log of the probability of the outcome. Okay. Expectation just means average. Okay, so averaged over all the possible outcomes, the negative log of the probability of that outcome. All right, let me write that out better. Okay? It's the negative of the sum of the probability of the outcome times the log of the probability of the outcome. Okay. This first time I saw this formula, I was like, okay, fine. And you've just written something on the board. Why should you believe me that that's an entropy? Only because it satisfies, the only reason is because it satisfies those properties I just said, okay? We'll just see. We'll see in a sec, okay? But essentially, logarithms turn multiplication into addition is the reason a log comes up, okay? If you think about combining 2 systems, this one has 4 possible configurations, and this one has 8 possible configurations, and the possible configurations of the combined system is 4 times 8, right? So it's multiplicative. If we want to turn that into something that's additive, we take the log, right? And we get 2 plus 3, okay? That's the only reason. That's where the definition comes from as far as I'm concerned. We usually use, in information theory, we use a base 2 algorithm, okay? It makes sense because we're usually thinking about bits, all right? That's not what's used in thermodynamics. So, what's the entropy of tossing a single coin? A fair coin, excuse me, yes, a fair coin. The formula is the sum of, all right. What's the first term of this for a fair coin? What's log of over half? Negative 1. Mm-hmm. Negative 1. Mm-hmm. Sorry, log 2, yes. We're always working log 2. Mm-hmm. Yep. Okay. So, equals 1 bit. Huh? Big surprise. Not a surprise at all. We know. We know what 1 bit of information is, no? Okay, so next. What's the entropy of tossing 2 coins? What are my outcomes? 2. Yeah. You know what? I know you know the answers too, okay? Come on. Okay, so we have a sum of 4 terms. We have a negative out the front, which is annoying. We have a sum of 4 terms times each of them has probability 1/4, if they're both fair coins, times log of 1/4. This is negative 2, so we have that cancels with that. There was a minus sign, goes there, and we get 2 bits, okay? So now I think you're convinced that this definition makes sense, no? It seems to make sense for how we measure information in classical computing, no? Now, I'm going to finish off this section by saying that one of the things I perhaps didn't emphasize enough there is that different observers can have different knowledge about the state of a classical system, and they're not really required to agree on a probability distribution. Okay? If you've already peeked at the result of that coin toss, then your state vector for this coin toss experiment is going to be different to mine. All right? Just thing to think about. So, 2 different observers might have a different probability distribution, might have a different vector psi, which represents the outcome of this experiment. Somebody might have tossed, Alice tossed the coin and got heads, but she didn't tell Bob the answer yet, right? So Bob's probability distribution is still, well, what's the best you can say? It's still half-half, okay? It's not deep, just an observation, right? Okay, time. Good. All right, so let's talk about processes. The main point I want to get out of this section is not that you understand stochastic processes. It's not part of quantum, not really. The main part I want you to get out of this is understanding how to write matrices and work with matrices in bracket notation, Dirac notation. So, I'm going to start out saying a deterministic process is one where if I give you an initial state, a well-defined initial state, when I'm writing this is going to be a basis state, right? We know for sure a final state. Okay? So, do I have an example on the next slide? Wow, okay. So, this process is a map with elements of the form initial to final for every possible initial basis state. Okay? By map, I mean function. So let's consider the operation of not tossing a coin. Sometimes I use that word wrong. Flipping the coin, okay? Turning it over, okay? What happens when I flip the coin over? Well, if I was in heads, then I go to tails. If I was in tails, then I go to heads, okay? Now I want to write down this process as a matrix. And this is the answer. And I want you guys to convince yourselves that that's the correct answer, that this matrix here has the properties we require of it, that applying it to heads gives tails, and applying it to tails give heads. Can anyone see that immediately? Maybe not. So let's do it. 1, 1, 1, 0. That's heads, okay? Good so far? So we got da, 0, 1, 1 hits there, 1. That's tails. Okay? And if I do the other, I'm not going to do the other. You can do that for yourself. Now, we're going to find a way to write these kind of matrices down using bracket notation. Let's consider something which in high school they generally don't do, which is called outer product. Outer product is the opposite of an inner product. Okay? So if an inner product is something like 1, 2, 3, 4, an outer product is something like 1, 2, I'm going to make my numbers easier for myself here, 1, 1. What is the shape? Is this a number? No, it's a matrix. What are the dimensions of the matrix? 2 by 2. Correct. So what is it? Kunk, kunk, 1. Kunk, kunk, 1. Kunk, kunk, 2, 2. Okay? Now, just to emphasize this, let's do it for a product of basis vectors. 0, 1, 0, 0. Am I going too fast? No. So this was a 0, excuse me. I'm sorry, my handwriting is atrocious. So when I get a product of basis vectors, I get like, I always get a matrix with a 1 in one position. All right, we're going to take advantage of that here. Well, we're going to take advantage of it in a second. First, setting that aside, we're going to look at how this outer product, H, T, acts on H. Now, H, T, acts on T. Tell me what the answer is. Stare at it. Tell me what the answer is for the first one. No, it's heads, but... Tails, heads, what's that? Sorry, it's not tails, it's not heads either. Sorry. Tails, heads is what? Tails, heads, the inner product of tails and heads is what? 0. Let me write it out. Okay, I can see lots of heads is, sorry, that's a kit. That is a bra. Sorry. Oh, that's a kit. 1, 0. This is a bra. 0, 1. This is a cat. 1, 0. This times this is 0. 0 times that is 0. Okay? What about this one? What is it? This is 1. Don't think of it in terms of sets. Tails, tails, the inner product of tails with itself is 1. So that final answer is heads. Okay? Are we good? Yeah, okay. It's tricky. Remember, we are multiplying a matrix, this is a matrix, by a vector. We've got to get a 0 or we've got to get a vector. Okay? Okay. So these guys here, outer products of basis vectors. Matrix operations are not commutative. If I started from the left, it would be something completely different. If I did, because I did. Okay, if I did, no, I wouldn't. If I did h times ht, then I would get the bra t. Okay, absolutely. Matrix operations are not commutative. Okay, so it matters. So the order absolutely 100% matters.
I think that's exactly the point. Like, why do you start from the left?
It's more conventional to work with cats than it is to work with bras. But you can. That's arbitrary. That's completely arbitrary. If you want to do all your quantum mechanics working with row vectors instead of column vectors, knock yourself out. Right?
No, I mean, so maybe, like, I'm just, trying to understand the whole process where I get lost is, like, here we're just writing some operations.
Yeah. Here we're doing.
Start evaluating like this, and I don't see an obvious reason why I should do this. And maybe, what's the point of this? Where am I trying to get with this? Like, maybe that answers my question.
We'll get there in a sec, okay? Where we're trying to get is we're trying to understand what these objects are and how they act on other objects, okay? We're just trying to understand what this does. We start with small atomic little things, and then we build up so we can do more complicated things, okay? Right now I'm going to get to the point, okay? Sure. Okay, so I have an outer product of basis vectors, all right? I've understood how that acts on things. Now, that gives us enough to be able to express a matrix like F in terms of these ket bras, in terms of these outer products. Okay? So, HT, just to go back to, I have to keep coming back to it just to make sure that everybody understands that these are just matrices, okay? This, I think we calculated and it was this. Hit row 0, column, yes. And TH, similarly, is going to be this one, right? And so this matrix F is, well, we had it before. It was 0, 1, 1, 0, which is equal to this plus this, right? Just to write it out with all the matrix, okay? So, as I've said here, we can now express a matrix in terms of these ket bras. This is useful, okay? You're just going to have to trust me that this is useful, all right? It is certain kinds of computations are way easier to do working with these guys, especially if I have a sparse matrix, than they are working with like a 16 by 16 matrix, okay? The important thing is I know what happens when I hit a tails ket with this guy, right? This 0, and that term vanishes, okay? So the collection of all these objects, which are outer products of basis vectors, are a basis for the space of matrices. Okay? Why do I care? I know I haven't mentioned quantum yet. Okay? Why do I care about matrices? We're going to see it. Okay? Why do I care so much about matrices? Because matrices are fundamental in quantum mechanics. For example, I can write the identity matrix, this is a formula that's used all the time, the identity matrix, 1, 1, 1, 1, 1, as the sum of all the ket bras with the same state in. Okay, so for example, I think I have an example on the next slide. For example, yeah, right. So for example, for our probability distribution with coins, the identity matrix is just written heads, heads, tails, tails. Is that clear? Yes? Everybody's nodding? Is anybody not nodding? You guys over there? Yeah, okay.
I mean, it's just like it's fast, so like
I know.
in less than time.
I apologize. We're gonna take a break in a sec, and let me get through this hour. Don't apologize. Don't apologize. I am going very fast. I know. I know. Okay. I'm going to skip the section on stochastic processes because I think we're just going to get bogged down in that, and it's not important. The only thing I would say about, we can also model stochastic processes with randomness in them using matrices. And the difference is that instead of matrices like 0, 1, 1, 0, we're going to get matrices like a half, a half, a half, a half. For example, that would be the matrix of tossing a coin. Okay? So what this matrix is saying is it doesn't matter what state I start out in, my end state is going to be half probability, okay? So that would be our coin toss process, okay? And the one point I want to make about this is that the columns of this matrix add up to 1 because probabilities have to be conserved, okay? I can't have a process which says that the probability of heads is a half and the probability of tails is a quarter, okay? That's not a good process. Okay? I have this constraint, the probabilities have to add up to 1. Why I'm emphasizing this? Because this is important once we get, I can't do the no cloning theorem without that understanding that not every matrix is a good process. Yes? The only difference between the deterministic process and the stochastic process is here I have ones, whereas here I have non-unit probabilities.
But I mean, so here what you are saying basically, it's like I'm gonna keep moving to states where I'm not certain about what's happening. I don't know, the Schrödinger's cat. I have the cat and this thing detonates and something happens, or there could be a different universe where it doesn't happen. That's more or less my understanding, right?
Yeah, you can look at it that way. Yeah, absolutely. But we're not in quantum yet.
But my point is just that if you look at it, you could say that every stochastic process is deterministic at the same time because you are
Okay.
determined to be in a superposition of the different things, right?
I understand. Right.
I mean, maybe it's
Sure. Okay, so in classical physics, in principle, with caveats, every physical process is deterministic if we have complete information about it, okay?
certain that this is the state that the thing is
Yes, okay. In practice, we can never possibly obtain perfect information about a system, okay? We are not doing physics here, okay? First of all, we're doing information theory, okay? Understand that when I'm saying when I'm talking about classical probabilities, I'm not talking about Newtonian mechanics, okay? I'm talking about classical probabilities as understood, because classical probabilities and quantum probabilities, perhaps I should start out by saying this. Classical probabilities and quantum probabilities are not the same, people. You cannot, I mean, I was going to say this, I have a slide about this later, but if you could express quantum probabilities in terms of classical probability theory, there would be no purpose to quantum computing, okay? The point is that quantum probabilities are different and cannot be expressed in terms of classical probability theory, okay? I want to say, we're not doing physics here, okay? A stochastic process is a thing in classical, in the classical world, right? The world around you is fundamentally classical, right? Things at this scale, okay? But we still have randomness, yeah? Okay. Yeah. Okay, another thing, we're not going to get into quantum foundations, okay? I'm really not going to go there, okay? That's okay. No, I understand. Yeah, yeah, I know. Okay. The point about this is that we have to conserve probabilities, and there will be a very similar constraint on quantum processes, which is also important. Okay. Here's where it gets difficult. This is the most difficult section of this, so I'm going to try and slow down a little bit, okay? We're going to talk about composite systems, okay? This is so important for understanding entanglement and everything else, and I'm scared to do this section because I realize it's a little abstract, okay? What if I have 2 coins? All right? My outcomes are heads, tails, tails, heads, tails, tails. Okay, I can model, I can construct this with what we've done already. Okay, I can fully model this. It's a probability distribution on these basis states. Okay, what's the psi I for each of these states? A quarter. Exactly. Right. So I have a 4 vector, 1 quarter, 1 quarter, 1 quarter, 1 quarter. Okay. But we can also view this as a composite system consisting of 2 coins that just happen to be put side by side. And I'm sorry guys, but we write this like this, with this scary looking multiplication sign. That's called the tensor product, or the Kronecker, or more strictly correctly, the Kronecker product, okay? It's a weird kind of multiplication. Let's see how it works. It's still multiplication. It still works algebraically like multiplication. So, we have 1 coin in the state, a half heads plus a half tails. And we have another coin in the state tails. Okay? That's the information we know about this coin, information we know about this other coin. The combined probability distribution, I'm going to write like this, okay? For now, I'm just writing a symbol on paper. Now, I told you it's a kind of multiplication, so let's multiply. So I have a half times heads, tails, times tails, right? It's going to follow the same rules of multiplication, and I'm going to multiply it out, right? Distributive rule. Let's write that in. Let me qualify. Most of the time, we barely write that guy in when it's clear. When we're actually internally in a calculation, we usually don't write that in. Okay, when we write formulas at the bottom, right, sometimes it's good to clarify that, okay? When we're actually calculating on paper, we usually don't write this guy in. It's usually clear. Okay, so we got heads times tails. And we've got tails times tails. Okay. So that's a half, and here's where we usually do an even further simplification. Is that the right answer? I'm going to define it in a second. I'm going to define it as something that works like multiplication. I'm not even going to define it. If you want to look up the, I'm not going to define it, but I'm going to show you how it works algebraically. Okay, just like physicists do. So yeah, that's correct. The probability is a half heads tails and a half tails tails. Okay, so that's correct. All right. Now let's do this one. All right? Multiply out again. Heads, 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 tails, tails, heads, tails, tails. Okay? We get 1 quarter, heads, heads. I'm just going to go straight to the answer. Plus tails, tails, plus tails, heads, plus heads, plus that one. Heads, tails. Okay, is that the right answer? Absolutely is. This is a quarter times all the possible outcomes. Okay, all right. This is all we need to do at this point. It works kind of like multiplication. All right. I should care. Okay, sometimes when we're doing these calculations, we get confused about which things belong to the first system and which things belong to the second system, so we label them with the states with A and B, Alice and Bob, right? Now if you want to see what a definition of it is, okay, I'll tell you how this relates to if I had matrices. Say I have half here. What was the first one we did? The first one we did was in tails, right? 0, 1 in tails, okay? How the tensor product works when we write it out like this is that this guy goes into here and into here. So we get 0 times a half, 0, 1 times a half, 0 times a half, 0, 1 times a half, which is, that's heads, that's heads, tails, times a half, plus, and this is tails, times a half, okay? So, yeah, okay, so that's if you ever want to do it with actual writing stuff out, it's like this goes in, like you take a copy of this and multiply it in there, a half times 0, 1, a half times 0, 1, and then you multiply it out, okay? We're not actually going to have to do that. Now, we can also make a state by taking a sum of two of these product states. And now here's where it starts to get interesting, okay? These states can't, in general, be factorized into a product of two states. So, for example, this example we did here, this state is factorized, okay? Into a state on, no, in fact, both examples we did are factorizable into a state on A, Alice's state, and a state on B, Bob's state, okay? But if we take sums of these, the result cannot necessarily be factorized that way, okay? So if we take this state, here we're saying, well, let's go through it. If Alice gets head, so does Bob. Or if Alice gets tails, so does Bob. But there's no outcome in which Alice gets heads and Bob gets tails. What do we call this kind of thing in probability? Correlation, exactly, perfect. Okay, I'm not doing a terrible job here. Okay? This is correlation. Okay? So when the states can't, and when they can be factorized into a state, into Alice's state tensored with Bob's state, what do we call that? Independence. Okay? Right? So the ability to be able to factorize these states comes back to the definition of what are of correlation independence in classical probability theory. All right? Yes? Oh, do I? Ah, shit. Yeah, okay. It's because, can I just unplug you here?
Yeah, absolutely.
Thanks. Now notice here, after observing a result for A, after observing Alice's coin, we know everything about Bob's coin. So the entropy of the whole system is the same as the entropy of either system in isolation. Okay, we have one bit of entropy in the whole system of Alice and Bob. We also have one bit of entropy in Alice's coin or in Bob's coin. You contrast this to the product state we had earlier, where after observing Alice's state, we know nothing at all about Bob's state. So the entropy of the whole system is the sum of the entropies of the isolated subsystems. Okay? This good? Yeah. Now, if we have processes, as we saw before, I can have a process that operates on, Alice and Bob might be in different places. Right? They don't have to be sitting next to each other. So if I have a process acting on Alice's coin and another process acting on Bob's coin, I might be interested in this combined process, right? And now we arrive at the tensor product of matrices, okay? A tensor product of matrices is what happens when you take two processes together and combine them together, okay? Often we label them A and B as well, and we get confused, okay? And here's how we do this, right? If I have the process X tensored with Y, acting on the states psi tensored with phi, then it's easy. The rule is simply this one, the one labeled A, acts on this one labeled A, and this one labeled B acts on this one labeled B, and the result is a tensor of the two operations. This makes sense, guys. Like this is intuitive. I know I'm writing this using a super confusing notation and all this, but it's also super intuitive. It's just saying, if I have a process acting on Alice's coin and a process acting on Bob's coin, if I take this combined process XY, and acted on the whole system, then the result is X acting on Alice, on Alice, and Y acting on the other one, on Bob, okay? Tensor together. So let's consider, right, so let's see how we do this. This is almost something we don't need to do. If you want to switch off for like 2 minutes, that's okay. So we had our two operations flip, the flip operation, 1, 1, and the other one, the toss operation. Yeah. Tensored. The rule for doing this is again similar to what I told you to do with vectors. Okay? You take this and you put it in there, take this, put it in there, put it in there, okay? So it's, what was it, 0 here. So 0 times all that, that's just 0 up here. 1 times all that is a half, a half, a half, a half. 0 times all that is 0 down here. 1 times all that is like a half, a half, a half, a half. Right? That's how you combine operate. That's no, well, yeah, no, sure. Yeah. Yeah, it's a 4x4 net matrix. Yeah. But this is an operation where I'm acting independently. This acts on Alice, this acts on Bob. Operations don't have to work like that. Let's consider an operation like this. I'm trying to do all this without once saying the word entanglement. And it's hard. Because I want to convince you guys, I want you guys to see what the actual difference between quantum and classical is, not what, not that you're going to think that correlations are entanglement. Correlations are not, correlations, classical systems can have correlations, right? So, all right, so we have a matrix which maps, what am I going to have at the front of this? What's my normalization going to be? I forget, let's forget about the number that sits out the front. I have heads, heads, mapping to heads, heads, plus tails, tails, going to tails, tails, plus tails, heads, going to tails, tails, plus, again, tails, tails, heads, tails, going to tails, tails, okay? Once again, you can see that this is doing this operation. If I start with heads, heads, what happens? This matrix comes in. I have heads, heads over here. This one with this gives 1. This guy survives. This tails, tails with heads, heads gives 0. Dies, dies, dies. And the result that survives is heads, heads. Okay? Do I just sound like a crazy person waving my hands? Or, well, I did, but does it make sense? Okay. Now, we can attempt to factorize this, right? I apologize if my handwriting on this is terrible, but look, we can factorize. We have a tails, tails, and a tails, tails, and a tails, tails here, right? So we could attempt to factorize this tails, tails out and have it acting, multiplying tails, heads, plus tails, tails, plus heads, tails. But then we'd be left with this guy here. There's no way I can factorize this matrix into a product like this, okay? And so the effect of this matrix is this process can create correlations. All right? Just because I didn't put it there. Yeah, yeah. Yeah, I'm just saying, this is a process. This is a process, right? Do you agree it's a legit process? I could, yeah, I mean, I can have that, you know? I mean, think of it writing, you can write a computer program which does that. Forget about heads and tails, right? Think about them as bits. You can write up, all right? And the point is that this can't be boiled down into an operation acting on the 2 bits individually, right? You have to have something in there which couples the 2 bits, okay? So for example, okay, I'm gonna steal my thunder and tell you that this operation might be called C naught, okay, if you have a CS background, right? Controlled not, yeah? Yeah. Okay, is it a tensor product? No, it is not a tensor product, okay. So it's about time we drop the charades, okay? A toss coin is really a classical bit with states 0, 1. So for the first time, I'm going to change the notation up on you. Our flip operation is called not, okay, in classical computing. In quantum, we call it X. I'll explain why in a sec. A bit string like this, so I can use this stuff to write numbers, right? Guys, like I can chain, you know, with tensor product, an arbitrary number of bits together, okay? And I get a bit string, and that's a binary number, okay? So the tensor product gives us a way to express numbers, which you already know. We use computers every day, right? We represent numbers as bits. All right, time for a first break. Let's see how many of you actually come back after it. It gets more interesting, trust me. This is like I know this was the painful, like, oh, Jesus. It's going to be more interesting, all right? We're going to get to quantum pretty soon. Well, after this. Go, take a break, all right? You have like 4 minutes. Anybody who's not taking a break, got any question? They want to? Yeah, I'll share the presentation. Yeah, I was going to say, can you guys somehow, I didn't get can you guys leave your email addresses or something somehow with me so that I can send you the presentation, but also I have a course notes which goes into more mathematical details, which I cannot get into here, but which actually goes through the math and gives you all the math you need for understanding quantum information, really, okay? And it's going to be a tough read, okay? It's it has proofs in it, okay? But it has everything listed out. And if you don't understand something I've written, that's fine, but you just go Google, you just ask ChatGPT, right? Or whatever, okay? To explain. Well, okay, yeah, sure. Yeah, my email is gavin.king@gmail.com. I need a drink of water. You can hear me fine. I don't need the mic, do I? Oh, no, because the recording shit. Okay, so first of all, complex numbers are much easier to understand than rational numbers or irrational numbers, okay? It's like, they're so much easier, okay? All you need is this one dude, I, who I squared equals minus 1. It's like the simplest definition you could possibly imagine. And we're just going to say that you can multiply I by a number, or you can add a number to it, okay? And that means that I can have these A plus IB, where A and B are real, is a totally legit number. And amazingly, at this point, I'm done, okay? We call A the real part of the number, and B the imaginary part, okay? That's the stupidest name I've ever heard. All numbers are imaginary, it's ridiculous. For no good reason, we call this a complex number, even though it's obviously like one of the simplest things you could possibly imagine. Very surprisingly, these complex numbers of the form I just wrote, A plus IB, are closed under all the usual operations of algebra, okay? Incredibly surprising, right? You wouldn't imagine that, okay? So for example, addition, well, that's easy to show, okay? If I add, 1 plus I plus minus 2 plus 2I, okay? If I expand that out, then I'm going to and use commutation, then I get 1 minus 2, and I get I plus 2I, and the result's that, just by using high school algebra, okay? Just treating I like I would any other symbol, okay? I go through a lot more of this in the course notes, okay? We're going to need something called the magnitude of a complex number, which is just like the length of a vector. We're going to need an operation called the complex conjugate. Now, physicists, because they like to be different, write the complex conjugate using a star instead of using a bar. And what does it do? Well, the complex conjugate acts on a real number and just gives the real number back, and it acts on I and gives negative I back. So when it acts on the whole of a complex number, you get A minus IB, okay? A useful relationship between these things is that the conjugate of a number, of a complex number times the complex number itself gives you the square of the magnitude. It's very useful when you want to divide complex numbers. Now, there's one way in which complex numbers are great, but there's one way in which they can make kind of shitty numbers, which is that you can't can't give them a total order, okay? So unlike other orders, other numbers, which you can line up arrange along a line, you can't do that with complex numbers. What you can do is you can draw them in a plane, where on one axis you have multiples of I, on the other axis you have the real part, so the imaginary part and the real part, and then every number you can put somewhere on the plane. I'm going to do something that looks kind of silly, right? I'm going to say that this angle here, I'm going to call it theta. And so we can write our complex number as z equals r. That's going to be the magnitude of the complex number. Okay, this if it wasn't clear, the length of this line is the magnitude of the complex number times cos theta plus I sine theta. Back to trigonometry. Who remembers which one's sine and which one's cos? Which one's this one? Cosine, exactly. Which one's this one? Sine, okay? All right. So cos theta is this distance along here, or r cos theta is this distance along here, and I times sine theta is this distance along here, right? Okay, so I can write that. This looks worse, no? Does look worse. Except then there's this amazing trick we can do, right? So we can write cos and sine as their Taylor series. Okay, so the Taylor series for cos is 1 minus a half theta squared plus other even powers of theta. And the Taylor series for sine is something with odd powers of theta. And so if we add these together, we get something like 1 plus I theta plus a half of I squared is minus 1 theta squared plus da 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 da. And this is this Taylor series for the exponential function. And so this, which looked awful, cos theta plus I sine theta, we can consider as the analytic continuation of the exponential function to the complex plane. What does analytic continuation mean? Doesn't matter. Ask ChatGPT later, okay? So in polar coordinates, we can write any complex number in this form. This is so useful. It's so much better than the A plus IB form. It's ridiculous. As a magnitude times e to the I, the angle in the complex plane. And in particular, some people get super excited about this relationship, right? If I set theta equals pi, then I get e to the I pi equals negative 1. And some people love it because they're like, oh, it has all these funny numbers like e and pi and I all in the same equation. Polar form for a complex number makes it very easy to multiply and exponentiate complex values because once again, we're coming back to the same thing that logarithms turn multiplication into addition. Even better, this may be going a little bit more, we don't actually need this, but if I write out this number, looks kind of complicated, right? And I raise it to the power of n, what happens? Well, I have the nth root of a here, so that's going to give me back, the nth root of a, the power of n is going to give me back a. This, I'm sorry? Hold on. Let me. This bit to the power of n, that is going to multiply this and is going to cancel out the n here, so I'm going to be left with e to the I alpha. And this bit where I have 2 pi I k over n, that's just going to be e to the power of 2 pi I k. Now e to the power of 2 pi times some integer, I integer, is just 1. So this term just drops out. This term is just 1 once I multiply this out. And what I get back is just a complex number in magnitude times alpha. What has this got me? This means that we immediately obtain n roots. For any n, for any integer n, we can write down n roots of any complex number just by introducing I squared equals minus 1. Suddenly, every number has n nth roots. This is completely surprising to me. I don't know. Do you guys think that's normal? That by introducing one number, I mean, one number that squares to minus 1, I would be able to find n roots of every n nth roots of any number. So the point of this is that now we have a set of numbers which are completely algebraically closed under nth roots. We can solve all polynomial equations. The roots of a complex number are arranged in a circle. Okay, they have a very regular structure. And that's all we're going to say about complex numbers. The point of that was really to say that we have this way of expressing complex numbers in the form magnitude times e to the I phase, what we call phase, an angle. Okay? That e to the I theta, we usually call that a phase. Okay, finally we get to talk about quantum states at last. Okay. So quantum states live in a complex vector space. So similar to classical probabilities, a quantum state is a superposition of the possible outcomes of an operation, of an experiment. For example, if I measure the spin of an electron, surprisingly, the only possible outcomes I will get is, if I measure the spin of an electron in the vertical direction, the only possible outcomes are up or down. Okay? So this has any, who here knows what electron spin is? You do. You do. Good. You do. Nice. Okay. Okay. So, all right. Good. I'm surprised. So spin is this. Okay. First of all, nothing's spinning. Okay. Spin is this intrinsic amount of angular momentum which is carried by any elementary particle. I'm talking about electrons, but I could equally be talking about protons and neutrons. I could equally be talking about quarks, neutrinos, any fermion, any elementary fermion, excuse me, has the same amount of spin, which is a half of h bar. Okay, we're going to work in units where h bar equals 1. H bar is actually a very small number if you express it in silly units that we actually use. So therefore, we can write the spin state of an electron as a vector. That's the probability of measuring spin up. That's the probability of measuring spin down. Okay, using exactly the same thing. Sorry, it's not. I lie. It is not. Spend an hour talking about classical probabilities. No, this is a number. Okay, and this is another number, and they are not probabilities. They're complex numbers. Definitely not probabilities if they're complex numbers. Okay. Not only are they not probabilities, they're not even real numbers. Quantum states belong to a complex vector space. Okay, so that's different to the vector spaces we were talking about earlier. The coefficients in a complex vector space are complex numbers. An inner product like spin up. Remember I spent like 10 minutes trying to convince you guys that these kind of inner products were these coefficients in the expansion. Okay, an inner product like this is no longer a probability of observing spin up, but it's a complex number called an amplitude. And to get a probability out, we need to take the square of the magnitude of that number. Okay? So this is how we get probabilities in quantum mechanics. We take the inner product of the thing the state we're observing, okay, the outcome we're observing, with the quantum state, and then we take its magnitude squared. Okay? Any questions about that? Do you guys know all this already? No. Yeah. Quantum state, a vector. A vector in a complex, a vector in a complex vector space. Okay? So it's again the same as the shit we were doing before with classical. The only difference is it has complex coefficients instead of probabilities as its coefficients. Yeah. And why I made such a big deal about all that when you guys were looking at me like, what the fuck is he even doing here? Okay. Because that's the thing that changes here, right? The thing that changes is that these are now these amplitudes, right? And there's a huge difference, right? This means that a probability distribution in a quantum state, is a completely different thing that can't even be represented in classical probability theory. Yes? I mean, it is arbitrary. It's called the Born rule. It's experiment. It comes from experiment. Yeah. I mean, because that's how the universe is. Okay. It's this rule. What I've written here. This has a name. It's called the Born rule, proposed by Max Born to explain how quantum mechanics are related to the outcomes of experiments. Okay. It's an experimental result. Okay. It's one of the. Yeah. I mean, I don't know. I don't remember what the postulates are. Is Born rule a postulate? It depends how you factorize them, probably. But this is, yeah. I mean, this is. No, because we did experiments, and that's how this was the theory that fitted the experimental results. No, of course it's not obvious. No. Yeah, it's a postulate. It's one of the, it's like, I don't know exactly this, but something slightly more complicated than this is one of the postulates of quantum mechanics, one of the axioms, right? It's one of the, the basic things which you assert, and which then gives you a theory which explains all the experiments. Okay? Yeah. No, you can't. I mean, you can't derive this from anywhere. Mm-hmm. Yeah, it's an axiom. Yeah. Okay. Now, in a complex vector space, we have a slightly different relationship between bras and kets. Instead of just being the transpose, the relationship between bras and kets comes from this dagger. All right? Dagger does two things. It transposes the vector, and it takes a conjugate of every element. Right? So if I have Good question, by the way. If I had a vector like this, that's a ket, and I dagger it, then I transpose, and I take the complex conjugate. So the complex conjugate of I is minus I, complex conjugate of 1 is 1, so I get that. All right? That's all. Easy enough. Okay? Just a little bit different. Okay? Ah, well, same thing. There's my 1 on root 2's, which I forgot to put over there, of course. The inner product, you guys would be used to the inner product of two vectors being symmetric, so that psi phi equals phi psi. But now, because of this whole thing, it picks up a complex conjugate, okay? Just something to watch out if you do find yourself doing calculations, all right? Now, once again, we have restrictions about the probabilities have to sum to unity. But in this case, it's not that coefficients that sum to unity. These coefficients are complex numbers. It's their magnitude squared which have to sum to unity, right? And that's the same thing as the length of the vector, the Euclidean norm of the vector. Yeah? Is that cool? No, I'm not seeing any reaction from over that side of the room. Does that make sense? Yes or no? Okay. So the length, so in this case, for quantum states, the length of the state has to be 1, okay? And that is just conservation of, that just says that probability, we're normalizing to a probability distribution over the states, over the basis states. So for our electron, we have these basis states up and down. And there the spin measured in the vertical direction. And the result of this measurement is going to be half and minus a half in sensible units. So how are we going to obtain the average value for a given quantum state? Now we're starting to get into it, guys. Well, I think you can see an average is a sum of probability of a state. Oh, sorry, the SI was negative a half. The result of the result of the measurement times the probability of that result, which in our case, we know it was the magnitude squared of psi up times a half, because the result is positive a half. Magnitude squared of psi down times negative a half. If I do the experiment many, many times, and I take an average, the mean value, okay? The yeah. With the which? No, this is, no. We're talking about in classical probability theory, the expectation. Physicists say expectation value for no apparent reason, okay? Sometimes people say mean value. Mean is a little bit, that word is a little bit unclear because it might mean an average over data, whereas with expectation we're talking about the expectation of a probability distribution. Yes? Yeah, that's because, here, yeah, I went too fast there. Oh. This thing is beeping at me and that doesn't work anymore. Okay. Okay. So I have this electron, right? I'm going to measure its spin. It's an empirical fact, okay? Just accept it, right? I'm not going to talk about particle physics. That you either get the electron is pointing up that has angular momentum in the up vertical direction of h bar over 2, or it has angular momentum in the negative z direction of negative h bar on 2. Okay, so those are the two possible outcomes of this experiment. Okay, experimental outcomes are numbers. All right, this is important. Experimental outcomes are not matrices, they're numbers, okay, real numbers, okay? So if I ask for what's the average, yeah, sorry, I skipped over the slide earlier. Physicists write expectations, averages. This is why you got lost, because I messed up and didn't explain the notation here, as something in angle brackets, right? This is the same thing as what I as a mathematician would write using an E, okay? It's just a different notation, and there's a reason for it, which you'll see in a second. Okay, so I have the probability of up times the amount plus h bar on 2, and the probability of down times negative h bar on 2. Yeah? You were asking, right? Yeah, okay, good. Now that's not the answer, right? Now if you squint, this looks sort of kind of like the inner product of psi and psi, okay? Because it has these amplitudes squared in there. So we're expecting that our formula for the expectation value of a quantum state is going to be something like this, but with something else. It's quadratic, okay? It's going to have a bra and a ket in there, but something else, because I want to somehow get amplitude squareds to get probabilities out. So what is it? What it is, it's going to be a matrix. So in quantum mechanics, observable things correspond to matrices. And the probability, the expectation values, mean values, averages, take this form, where this is a matrix representing that observable. This is the bra, this is the ket of the quantum state. So now let's see what was the right matrix for our case of spin in the vertical direction. Shit. Wow. If we go back a couple of slides and we see the formula I said before, you see that the answer has to be, well, that matrix there, 1, negative 1. Probably. Let's compute it. For the quantum state down, okay? Let's say I've got a quantum state where the electron is pointing down, right? What's down, SZ, up? It's, down. It's 0, 1, 1, negative 1, 0, 1. Zero, 0, negative 1, 0, 1. Sorry, there was a half here. Half times negative 1 equals negative a half. Sorry, this is atrocious. I don't know how to write on things, on vertical things, but you can see we get the right answer out, okay? If we calculate this with the matrix I just told you was the matrix of SZ, spin in the vertical direction, on the spin down state, then I get out the right answer for the expectation value. Okay? Yes? No, okay. We'll see in a second. Okay, that seemed like what he just said. What was the point of that? What was the point of writing this as a matrix when I could just calculate like I did before, right? So finally we arrive at something completely unique about quantum mechanics. That should say vertical. Oh no, sorry. If I have an electron pointing up, And now I measure its spin along the horizontal direction. What should I observe? First of all, what does your classical intuition tell you that you should observe? I have an electron with its angular momentum pointing up there, and I measure what's its angular momentum along there. What would your classical intuition tell you you should measure? 0, precisely. What do you actually measure? 50% of the time, you measure it's pointing that way, and 50% of the time, you measure it's pointing that way, by exactly h bar on 2. Now what happens when I measure it this way, and I come back and measure it in the vertical direction? What do I get? 50% of the time it's pointing up, and 50% of the time it's pointing down. Now, I'm not going to get deeply into this aspect of particle physics, right? The point is that these are what we call incompatible observables. All right. Once I measured it, if I measured and found that this is in the spin up state, I have no information at all about what its spin would be in that direction. Okay. In fact, it's not even sensible to, it's not that I have no information; it's that there's no information to be had in a sense. The act of measurement. Well, okay, I'm not going to get into that either. One way of thinking about it is that the act of measurement has changed the state, right? Another way of thinking about it is that I really shouldn't get into this. I've entangled myself with the state. So if we know exactly the vertical spin, we have 0 information about the horizontal spin. So now we want to ask, how do I represent horizontal spin as a matrix? And look, we come back to our friend we had before. Okay, this is just half times the what was I calling it? F, yeah, the x, exactly, x. Yeah. Yeah. Now you see where x comes from, right? Okay. So I don't know if I need to do any calculations with that. Will you guys just trust me that if I stick this, if I stick this in between an upspin state, half, 1, 1, well, let's do it, because I went through all that work of, so let's see, hold on, I'm going to actually stand in front of it and write properly. So here we have half, that is up, down. Okay, so that's that matrix. Remember, I went through all that work to explain to you how to write matrices in this form, okay? That's the same matrix as that one, okay? So this guy comes in, hits this, produces 1, and we're left with that. Comes in, kills that. Something's wrong here. Oh, no, this is right. This guy comes in, okay, this guy hits there, produces 0, okay? That term drops out. This guy comes in, produces 1 here. No, something's wrong. Oh, yeah, no, that's correct. Comes in, hits this here, produces 0. This term drops out, and I get 0 as the expectation value of xx on the state pointing upwards, which is what we knew. We said half the time it's that way, half the time it's that way. Okay? Did that make it all any sense, despite my confusing myself about it? Yes. Yeah. Okay. So we have 2 directions in which we can measure spin in. And they each correspond, they're different observables. Spin in the vertical direction, spin in the horizontal direction. It's actually 3, but okay. One of them we said it corresponds to the matrix, to this matrix. Okay? Called Z, by the way. The other one, we said it corresponds to this matrix. No. Here we're not talking about composite systems. We're talking about I was trying to not use this word because it's going to come up in a second. We're talking about incompatible observables. That this observable spin in the vertical direction and spin in the horizontal direction are fundamentally incompatible, okay? You can't, if you have information, if you measure this, and I'll make that precise in a second, right? What that means. I was just trying to show you that this definition of this matrix is sensible in that I get the right answer out. What's the right answer for the average it's 0, okay? I'm not trying to prove anything, okay? In many ways I simply can't prove this. These are things that derive from experiment, right? Yes, maybe I can if I look at these are the bases of the SU2 symmetry group, okay, if you must know, right? I'll come to that in a second, but I'm not going to get into group theory either. So just trust me that we have these two matrices representing these different observables, and if we evaluate expectation values, if we take measurements on the same quantum state with these different matrices, then we can find out what we expect to get out of the experiment. Okay, that these matrices represent these things I can measure. Okay, that's all I want to say for now. Okay, I'm not going to derive that this is correct. I just wanted to make it plausible that this matrix might represent that observable. And we did that. So the question is then, which matrices represent observable quantities? And here, I come back to something I said a second ago. An observable quantity we take to always be a real number. Okay, it can't be a complex number. Now, I don't know what your high school teacher told you a matrix is. But the best way to think about a matrix, the way matrices were explained to me in high school was absolute garbage, and I have no idea why I even went along with it, okay? The best way to understand a matrix is it is a linear function. That's all, on a vector space. That's all, it's a linear function, okay? It turns out that any linear function can be written as a square and some numbers, okay? Just because finite dimensional Hilbert spaces are all isomorphic to, to the given dimension, they were isomorphic. So we can ask, which directions in space, so if a matrix is a transformation of space, a linear transformation, which directions in space, in that vector space, are left invariant? Okay? By invariant, I mean they don't get, what's that called? Rotated. Okay? So which directions, okay? If I apply this matrix to this space, right, I have a vector sitting in this space, some vectors are going to be rotated. Some vectors are going to be left pointing in the same direction. They might be scaled, yes. These directions are called eigenvectors. How many people know what this is? Good. You all should know because it's huge in machine learning and yeah, right, okay. So, by the way, eigenvectors and eigenvalues are far more beautiful in complex vector spaces than they are in real vector spaces, okay? The machine learning, I sit there and and I'm like, what the hell is he saying? That's not right. And then I think, oh yeah, it's right in real vector spaces and it's ugly, it's disgusting. Complex vector spaces are much more beautiful. So these are called eigenvectors, right? So I have some matrix, it acts on a ket, and I get the same ket back scaled by some number, which can be complex. Okay? Does anybody need a better explanation of what eigenvectors and eigenvalues are? Somebody who didn't know who didn't know what they are? You guys, okay. So, An eigenvector is a vector, any vector, which it's associated with the matrix. Every matrix has its own eigenvectors and eigenvalues. I hit the vector with the matrix, and I get the same vector back multiplied by a number, okay? That number, which can be complex, is called the eigenvalue, and that vector is called the eigenvector, okay? That's all. Okay, so transformation simply rescales the eigenvector by a complex number. Now, consider these two matrices. This one, its eigenvectors are the basis state, 0, 1. That corresponds to it being, that fact corresponds to the matrix being diagonal. Okay? You can check that if you like. This one, its eigenvectors are much more complicated. They're actually the states we usually call plus and minus. And you can't immediately see it's much more complicated, right? But these two matrices both have the same eigenvalues, 2 and 3. In some sense, and their eigenvectors are orthogonal to each other. So in some sense, these are the same matrix written in different bases, okay? In some sense, you can say this is the same operation, but I've just changed my coordinate axes. Okay? That these matrices are connected by just a rotation of my coordinate axes. In some sense, they're the same thing. They're the same matrix. In fact, we much prefer this representation where it's diagonal. We can just read the eigenvalues off. And so half of physics involves diagonalizing matrices. Okay. If you have not watched this, okay, there's this video, like a couple of 10-minute or something videos on YouTube by this guy, 3 Blue, 1 Brown, which explain all this shit way, way better than reading a whole linear algebra book. Yeah. Highly, you're right, yeah. Highly recommended. Now, coming back to the question, which matrices represent observables in quantum mechanics? It is a mathematical fact that the eigenvalues of a matrix are all real if the conjugate transpose of the matrix is the same as it gives you back the matrix, okay? These kind of matrices are called, anybody know? Called Hermitian. Oh. Yeah, okay. These are Hermitian matrices, right? So you can check. Well, I probably got that as my next thing. Oh, no. Okay. Are these matrices Hermitian? Yeah, they are. I mean, first of all, they have only real values in them, so the conjugation does nothing to them, and you transpose this, or you transpose this, you get back the same thing. Okay? So they're observables. The eigenvalues of the matrix we interpret in quantum mechanics, again, this is a postulate, right? This is, I can't prove this to you, right? The eigenvalues of the matrix are the possible outcomes of a measurement. So over here, we have a diagonal matrix, okay? Really, this came with a half out the front of it, if you remember, okay? What are the possible outcomes of this measurement of the spin in the z direction? Half, negative a half, right? Yes? Are you guys with me, or? Okay. Yeah, I'm saying an exercise. Show that the following are the eigenvectors of this one. I feel like I'm going slow at this point, but perhaps this one is still worth doing. Let's do it. Okay. So Sx was, what did it have? A half, right? Yes. So that's Sx, and I'm going to act it on this vector, which is 1 on root 2. Okay? This acts on this. 0 dies. This acts on this. I get... I'm going fast here, but I hope you guys can see. This acting on this gives me up. Yes? Because down, down is 1. This acting on this gave me 0 because down, up is 0. Now I have this acting on this. You're going to get down. This acting on this is going to give me 0. Have a half out the front here. I also have a, 1 on root 2. Yeah, it's fine. I'm not sure about my numbers here. Whatever. Numbers don't matter for the... Oh yeah, it's correct, yeah. Equals a half times 1 on root 2 times up, down. That was the state I started with, okay? This state. This state. And so that, this state. So the action of this matrix, Sx, on this state, left or whatever, was to multiply it by a number 1/2. Okay? So this state is an eigenvector of Sx. Okay? So now we've shown how to represent, now we know how to represent these states I was saying before of left and right. They're these states. Okay? Up and down we already knew. They're the states 1, 0, 0, 1. Yeah? Left and right, or are these states plus and minus? Oh, yeah. Sometimes you usually, left and right, I'm calling them here. Okay, they're the eigenvectors of Sx. The other one's the eigenvectors of Sz. Okay? It's just a fact, okay? But you can see it there. Are we okay? Okay. So we were always doing, you hand a physicist 2 matrices, the very first thing they're going to do is find the commutator. Okay, the commutator is this thing, AB minus BA. It's a measure of to what extent do these matrices not commute with each other. So let's calculate it for SZ and Sx. So we have 1 minus 1, 1, 1, minus 1, 1, 1 minus 1, 0, 0, 0, no, that's not right. Wait. Sorry, 1 here, negative 1 here, 0, minus 0, negative 1, 1, 0. Oh God, I ran out of space. 0 minus 0 is 0. 1 minus minus 1 is 2. Minus 1 minus 1 minus 1. Minus 1 minus 2. Minus 2. And 0. Is that the answer I was expecting to get? It's not actually. Yeah, it is. Okay. Yeah. I'm missing some halves and stuff around there, but no, that's correct. So this is, yeah, that's correct. Okay. So these matrices don't commute, all right? There's a difference between AB and BA. This corresponds to what I said before about these being incompatible observables. So if the commutator vanishes, if that commutator is 0, then A and B would have the same eigenvectors, which means that we could know the value of the observable quantity of the two observable quantities simultaneously. In our case, that commutator does not vanish, and we cannot know the value of both of these observables simultaneously. Okay? So you might have heard, if you read about quantum mechanics, that famously momentum and position are non-commuting observables. You cannot know the position and the momentum of a particle perfectly at the same time. Okay? But here, we see this. What, no integrals, guys? We just calculated the commutator of two matrices, two by two matrices. Okay? This is and it's no difference to what's going on with position and momentum, okay? Just there we're in an infinite dimensional vector space, whereas here we're in a two-dimensional vector space. Okay? But it's exactly the same thing that's going on, right? And the point is that if A and B have the same eigenvectors, then we can write those matrices in the basis of those eigenvectors, and they're both diagonal, and we can see the eigenvalues in the diagonal form. So I said half of physics about diagonalizing matrices. So in the case where matrices don't commute, there's a fundamental limit to how precisely we can measure both observables simultaneously, and it is this, the famous uncertainty principle, okay? Written correctly, okay? The uncertainty in A times the uncertainty in B has to be greater than a half, whatever, times magnitude, the expectation value of their commutator. Okay, if the commutator vanishes, then they can both be known precisely. If the commutator does not vanish, then we can't know them both perfectly. Over here, we have a non-vanishing commutator. We can't know the spin in X and the spin in Y simultaneously. Spin in Z and spin in Y, in X spin simultaneously. All right. Going late, but let's. Do you guys need another break? No? Okay. All right. Okay. My favorite topic is entanglement. I love it. It's awesome. An electron spin is just one example of a two-level system. Okay? Now we want to go a bit more abstract. I was talking about electron spins because I thought it's something kind of, a little bit that you can at least a little bit sort of have some physical intuition about. Now we're going to do another change in notation. Instead of writing up and down, we're going to write 0 and 1. Okay? And you now have permission to call this a qubit. We're going to call these states left and right. Left and right was a super ugly notation, but we're going to call them plus and minus as God intended. And we're going to call these observables SX and SZ instead of, these ones with this annoying half out the front of them, which I kept forgetting about. We're going to talk about X and Z, which are 2 times that matrix. And in fact, they have a friend, Y. And you might as well just memorize these 3 matrices right now because anything quantum, you see them over and over again. Okay, what are they? These are called Pauli matrices. And in terms of electron spins, which we were talking about, this is the observable corresponding electron spin in the X direction, this in the Y direction, and this in the Z direction. Okay? Written in the basis of the eigenvectors of Z. Okay? If we rotate our coordinate bases, those vectors get those matrices get permutated. Okay? Permuted. Okay. Is Y Hermitian? Hermitian are complex matrices. Hermitian is actually the definition. Hermitian is the equivalent of symmetric for complex matrices. Hermitian means, if we recall, the question is Y dagger equal to Y, where dagger is a conjugate transpose? Let's transpose this first. What happens? Yeah. Now conjugate it. so it's Hermitian. Okay. All three of those matrices are Hermitian. They're also unitary. They have so many beautiful properties. They're also a basis. Those three matrices form a basis for the vector space of 2 by 2 Hermitian matrices. Together with the identity matrix, they they're a basis for the vector space of Hermitian matrices, 2 by 2 Hermitian matrices. Now, back earlier, I wrote down, I hope you remember, I wrote down this state, and I said that that was a correlated state, okay, when we're talking about classical probabilities. Now that we're talking about a quantum state, now we have permission to call that state entangled. So Alice has a qubit, and Bob has a qubit. If Alice measures her qubit, and it comes out 0, then so must Bob's qubit come out 0. Similarly, if Alice measures 1, Bob measures the same. Do I have time to do this? This is kind of long and a little bit tedious. Let's skip it, okay? Let's skip it. It doesn't matter, I'm not showing anything. Now, it can be shown, right? We're not going to do it. That this quantum state, even though it's exactly the same as the classical, or superficially the same as the classical state I mentioned before, but remember this is an element of a complex vector space, not an element of a real vector space, has correlations which are strictly stronger than classical correlations, in the sense that no probability, there is no joint classical probability distribution which can represent the correlations in that quantum state. Okay? I can't prove it, but if you want to look it up, look up the CAS-HS inequality. This is an inequality which must be satisfied for every pair. Well, it's a little bit more complicated than just two classical variables, but there's 4 of them. For any classical random variables, these things are like correlations, okay? They must satisfy this inequality, and it is straightforward to show, like 3 lines, to show that this state we just wrote up here does not satisfy that inequality. And so therefore, quantum probabilities are not classical probabilities. Right? And this is called a Bell inequality, right? And it has been, it has been experimentally observed, okay? It was I don't know how much of a history I want to go in, but the EPR, you might have heard about Einstein publishing a paper with Podolsky-Rosen paper where he argued that quantum mechanics must be incomplete because yada, 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 yada. Sorry? The what? Yeah, hidden variables. Yeah, exactly. And this guy, John Bell, showed that, in fact, quantum mechanics had things which couldn't be explained, admitted things which couldn't be explained by hidden variables, right? And that if you could experimentally observe violations of inequalities like this, right, then that would prove that, that Einstein was wrong, okay? Like Einstein, in being wrong, was the most, had so much insight and created this huge, massive field of, called quantum information out of his being wrong, right? So, damn, I would love to be wrong in that way. Every single physics student knows what the EPR paper is, right? So John Bell said, showed that there were these inequalities which could be violated in quantum mechanics, and then later they were experimentally confirmed. Okay, and the whole idea of quantum computing is to somehow take advantage of this. Right? If quantum computing was nothing more than if quantum systems could be simulated by classical systems, right? By classical, then we could not possibly hope to obtain an exponential speedup, right? The only reason we can in certain problems is because quantum probabilities are not classical probabilities. Um, and we'll see in a sec, hopefully we will see, still have about 40 minutes, that any advantage does not come from superpositions. And I hope that's clear now, right? I hope that all the work I went through to talk about classical probabilities and how they're superpositions of these states shows you that the difference between quantum and classical is not superpositions, okay? It's a little bit deeper and more subtle than that. It's in these complex numbers somehow. All right. Do we need a break or are we going to power through? We're getting there, all right? We're actually really getting there finally. So, a state of a qubit is given by two complex numbers, remember. Okay? Two complex coefficients capture the state of a qubit. Saying the same thing over and over and over again. But we also have a constraint that the state must be normalized, okay? So we have that constraint. Remember, each of these has two real numbers in it? Yes. Don't quite know how to answer it. I mean, in a sense, you can set those numbers to be whatever you like and just say, and just normalize them after the fact, okay? I mean, it's not so much a constraint as you're going to observe an outcome, right? And you want to know how often you observe that outcome compared to that outcome, okay? There's no cases in which I just lose an outcome, which the outcome is just, I mean, there can be, in the theory of open quantum systems, this constraint is relaxed because sometimes, I don't know, I just lose some probability, right? Some things into the, okay. I sort of don't know how to answer the question in the sense of, because in a sense you don't have to normalize. Sometimes we do it with non-normalized states, right? But in terms of asking, in terms of coming back to the if you don't want to say the prevalence of an outcome, ultimately you can map those back to probabilities, right? And so ultimately what you're interested in, the number of degrees of freedom I'm trying to explore the degrees of freedom in the system, right? Is going to come back to the same thing. Does that sort of answer the question? I think that's almost sort of, so the trouble is I'm not an expert in this. I know in open quantum systems they do allow kind of loss of sometimes, but it's more sort of like, oh, you just didn't observe that, Yeah. So, somehow, I mean, something had to happen in a sense, right? I mean, it's like, yes, quantum probabilities are not classical probabilities, but in the end, quantum mechanics, just quantum mechanics, a regular bog standard, it does give you probabilities at the end. That is the point. We are supposed to get probabilities at the end. At this one, that we have probability of a half of spin up and probability of a half of spin down, right? Okay, and that just says, if I observe 1,000 times, if I measure 1,000 different electrons, I'm going to get around about 50% of them up and around about 50% of them down, okay? So it's still, I don't know if that answers the question, but it's, okay. All right. So, I had four real numbers, two real numbers in alpha, two real numbers in beta. I put one constraint on them, okay? And now we come to a little subtlety that's actually incredibly important, right? That the effect of multiplying any quantum state by a phase, a quantum phase, has no effect on any observable. The reason for that is, well, you know, we can see it here. What's the expectation value of some observable? Okay, now let's take this state here. If I dagger this to get the bra, I'm going to get e to the negative I theta. Okay, that's the complex conjugate of this one, right? So I'm going to get psi e to the negative I theta times the observable. Sorry, I wrote that in the wrong spot. It should go there. E to the I theta times the state. These are just numbers. They go through and they cancel each other out. Okay? So there is an overall phase. Multiplying a vector, multiplying this state by a phase, e to the I theta, does not affect the result of any experiment. Okay? It kind of get, you know, because everything's always squared when you calculate anything observable. There is like this sort of mathematical, what's the correct word? Not ambiguity, the opposite of ambiguity. Gauge symmetry is the only word that's coming to mind, but redundancy is the word I'm looking for. There's a redundancy in our representation of the quantum state, okay? There's an overall global phase in any quantum state, which is irrelevant. So now where I started with 4 degrees of freedom, I got rid of one of them from this constraint, and one of them is redundant. Sorry, that was that. That derivation I just wrote super ugly there is this derivation, okay? You can check it later. You can convince yourself that's correct. That multiplying psi by e to the I theta gives me the same result back. That phase is related to like the whole existence of electromagnetism, by the way. I'm not going to explain what I mean by that. So finally, our qubit has only 2 degrees of freedom, right? It lives in a state of our qubit lives in a 2-dimensional manifold, okay? Now, we want to know what's the geometry of that manifold, okay? We have 2 degrees of freedom, we can move that way. What is its geometry? Well, we can do a very common trick that physicists use, which is when they have some numbers which are constrained by some constraint, they write it as an angle. So here the constraint is this, right? Now you remember from high school, this identity, cos squared theta plus sine squared theta equals 1. Okay? Looks a lot like this. If we make cos theta be magnitude of alpha, sine theta be the magnitude of beta, okay? Then theta somehow captures alpha and beta at the same time. But these are complex numbers, right? And so there's another degree of freedom there, but there's not 2 degrees of freedom because of the overall phase, okay? So once we cancel out the overall phase, you can think of this overall phase sitting out here multiplying the whole thing. What we have is this angle theta, and then one phase which is the relative phase between the 2 states. Okay, we start out with four real numbers. You can think of them as 2 magnitudes and 2 complex phases. And we reduce that down to 2 degrees of freedom. This is just math here, okay? It's just mathematical tricks, okay? The point is that I can write this like this. Now, this should look like polar coordinates of something. And indeed it is. The geometry of a qubit state is a sphere. Actually, it's a slightly sweeping one little wrinkle under the carpet. So our states 0 and 1, or spin up, spin down, are the north and south pole of our sphere. Our states left and right, or plus and minus, are these states pointing out and into the page. And then there's 2 more states, which are the eigenvectors of the Y matrix, the one with the I's in it, which nobody can ever remember which gets the negative sign. Right? And so it's a sphere, and this corresponds to it really is this geometry when you think about spin states. Okay, spin states are up, down, left, right, in, out. Okay. By any qubit, Any two-level, a qubit is an abstraction over any system with what we call two-level systems, right? Any two-level quantum mechanical system has this as an abstract geometry of its states in an abstract sense. Okay, it doesn't need to actually represent directions in space anymore. If we're talking about excitations of a well, let's talk about a real actual flux qubit or something, right? That's they're superconducting currents moving in different directions. Okay, it doesn't matter. That's in this case is something super abstract to think about this block sphere. Okay, but we can still think about it in that sense. There's one way in which is a little bit misleading. Okay, 0 and 1 are orthogonal. Okay, and we put it at the north and south pole. In the normal symmetry group of our space SO3, right, the north and the south pole are parallel, okay? Those directions are parallel. And these directions are orthogonal to the up-down directions. In this case, in the block sphere, this is not orthogonal to that, okay? So I perhaps should have said that its topology is spherical, but its geometry is something a little bit different, okay? Its symmetry group is SU2. I'm going to skip over that. Well, maybe I'm going to say it. Another super weird thing about this is if you make a 2 pi rotation, okay? So in ordinary space, if you make a rotation of 360 degrees, you get back the same state. On the block sphere, if you make this same rotation, you get back the negative of the state. Now, if we just have one qubit, that's nothing because that's just a global phase and its effect is irrelevant. If we have 2 qubits and we rotate one of them by 360 degrees, we do not get back the same quantum state. And yeah, I mean, apparently that's how electron spins actually work. It's crazy, right? All right. Quantum circuits. A quantum process, we saw earlier we had deterministic and stochastic processes, and we said that the process must preserve the length of the vector. Well, no, we said that had to preserve something else in the classical case. In this case, in quantum case, the vector has to be length 1, which means the process, to conserve probabilities, which means that the process must conserve the length of the vector. Okay? It looks like I'm losing a lot of people here. Are you lost? Yes? Okay. Where do we get lost? On the block sphere? Here. Okay. 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 So what's a quantum circuit? It's a process acting on qubits. No? Before we had processes which acted on coins. We could turn them over, we could toss them, we could consider 2, 3 coins together as a tensor product. Okay? A quantum process is a process which acts on quantum states, on qubits. Okay? And we want to find out what they can do. So why do we want to do this? Well, we want to use qubits, we want to use quantum systems to do computation. Okay? And the analogy they kind of use is circuits. Okay? It's a stupid word because the process we're actually considering are linear. There's no loops in them. Okay? So a quantum circuit is applying a series of evolution matrices, it turns out. Okay? A series of changes, and before we modeled processes as matrices. Okay? So a quantum process, a quantum computation is going to be essentially boiled down to a matrix which acts on qubits. Yeah? Okay? Yeah? Are we unlost now? Okay, let's go a bit and what I'm saying, it has to preserve probabilities, okay? We want probabilities summing to 1 coming out at the end. So it's got to preserve the length of a vector, okay, which corresponded to the sum of probabilities. Yeah? Now, The matrices which are like that in a complex vector space are called unitary matrices. Okay? And they are identified by the fact that they satisfy that property there. Okay? U dagger U gives me back the identity matrix. Okay? It's just a fact. Okay? All the eigenvalues of these matrices which satisfy that, it's easy to prove, I'm not going to do it, have magnitude 1. And that means that they don't make vectors longer or small. Okay? If every eigenvalue has magnitude 1, then whatever direction I pick in space, it can be rotated, right? But it can't be stretched. Okay? Yeah, make sense? Yeah. Okay, so unitary matrices are the ones we're interested in. Okay, they can add phases to things, they can do rotations, and much more complicated things. We're in a complex vector space. Don't trust too much your intuition coming from a real vector spaces, right? But yeah, those are the matrices, the unitary matrices, the ones which satisfy this. Yeah, as I said, every eigenvalue has that. Are the Pauli matrices unitary? They are. Okay. Easy to check, easy to verify. Do it at home, okay? So the Pauli matrix is a unitary and Hermitian, which means that they're perfectly good quantum processes, okay, for a qubit, right? In fact, they're very common. They're what we call quantum gates. Some of the ones are Pauli matrices, or some of the quantum gates. So, how do they act on the Bloch sphere? X is a rotation of pi, 180 degrees, around the x-axis. Y is a rotation around the y-axis, and z is a rotation around the z-axis, around the vertical axis, okay? I'm not going to show it because we're running out of time, but that's what they do. You can validate this. Here's another matrix which is very common called the Hadamard matrix. This is also unitary. We are going to do this one. Yeah, 1 on root 2. I think that's supposed to be 1 over 2. I got messed up there. So, how does this act on 0? Okay, good. This equals 1, 1. No, it is 1 on root 2. Okay? So it takes this state and produces the state 1 on root 2, 0 plus 1, which is the state we've been calling, or we are now calling plus. Okay? That's a very useful gate, the Hadamard gate. Cool. So H turns out to be a rotation of 90 degrees around the y-axis. So if we draw the Bloch sphere here, so it'll take this state here, as we just saw, to here, okay? And in fact, it turns out that all these gates acting on qubits, that's all they do. They do rotations in the Bloch sphere. Which means that we can't create entanglement using single qubit gates or even tensor products of single qubit gates. So that comes back to the thing I was talking to before, okay? A tensor product of operations, okay, operations that act on one qubit at a time, can't create correlations, okay? They're just going to leave us with another product state. Yeah? Remember we said entangled states, correlated states are those states which can't be factorized. And single qubit operations acting on a single qubit one at a time, are only going to produce other states which are factorizable. So cannot produce entanglement. To produce entanglement, which we're going to have to do if we ever hope to get anything useful out of quantum computing. Yeah, sure, we can emulate classical computing on qubits, which are like, millions of times slower, as much as we like. Probably more than millions of times slower, I don't know what it is. We're going to have to take advantage of entanglement. So we're going to need a gate which acts on 2 qubits at the same time, okay? And that is the controlled NOT gate. And what happens here? This says, we have a control qubit and a qubit that we're acting on. If the control qubit is in the state 0, we do nothing. We leave the second qubit alone. If the control qubit is in the state 1, then we hit it with a NOT operation. So we flip it. So we can write this as a matrix, just like this. I think we've done like a lot of this before, so I'm not gonna write it out. This says, essentially, if the first bit is 0, we leave the second bit alone. This says, if the first bit is 1, we flip the second bit. Yeah? Or we can write it out like that, and it looks like that. Same thing. This is the same as okay, or we can write it like that. Another way we can write it is the sum of two tensor products. Okay, again, this says, wow, do I need this actually? Yeah, well, the point is to say that this can't be factorized further. All right, now we're getting to it. The circuit I'm going to consider is the one which applies a Hadamard to the first qubit and does nothing, the identity, to the second qubit, and then acts on it with C0. So let's do the first step of this. This is a product. So the Hadamard acts on the first qubit. The identity does nothing to the second qubit. I really wish I had my clicker here. And so the combined effect from the rules I showed you guys earlier about how tensor product operators act. I get that. That puts the first qubit in the plus state. Okay. So we rotated it round. First qubit is, both qubits started out up here. We've rotated it round now so that it's down here. And the second qubit is still in its original state. Now we're going to act on it with C0. Remember, C0 says, if the first qubit is 0, I'm going to do nothing. If the first qubit is 1, I'm going to do something. I'm going to flip the other one. But now, the first qubit is in the superposition of 1 and 0. So we have to consider the action of C0 on this plus state, with the control qubit in the plus state. So we multiply that out. Now we have C0 acting on 0, 0, and C0 acting on 1, 0. Okay, so this one, what's going to happen to this guy? I've lost everybody. The controlled NOT operation says, if the control qubit is 0, do nothing to the second qubit. If the control qubit is 1, flip the second qubit. Okay? C0 is an operation which kind of mixes the state of the two qubits, right? Creates correlations between them. So the result of this is that in this case, in this half of the state, we just get the identity. In the second half of the state, we get the X, we get a NOT. And the final result is that we get out this beautiful entangled Bell state. Okay, so we used this quantum circuit, that's how we write it graphically, to create a Bell state, to create entanglement. This is the C0 gate. This is the Hadamard gate. So we have 2 qubits coming in here. First, the Hadamard acts on this control qubit and turns it and rotates it into the plus state, a superposition of 1 and 0. Then we come through, we use this this superposition state as the control on a C naught, and because it was in a superposition, right, of 1 and 0, when it acted here, what came out at the end was an entangled state that can't be factorized. Okay, so this is how you can create. This is the basic way to create entanglement in a quantum circuit. Seeing, I don't know what sort of stairs. I know it's been a lot. Yes. Yes, but I don't understand the question. Let's do it this way. So we start out, let's look at what's happened to the first qubit, okay? We come in with 0. We hit it with Hadamard. Then at this point, what we have is a state plus, which is a superposition of 0 and 1. Okay. Now let's consider what happens to this is A and this is B. This one, nothing happens to it at the first step. Then it hits by this control not operation. Now, what the control not, we would know if this was 0, if the state here was still 0, we change it, but it's not. If the state here was still 0, then it would do nothing. If the state were 1, then it would flip this guy, act on it with an X, okay? It would reverse the qubit. Yeah, the second one started out in 0, okay? Now, if I hit 0 with not, what do I get? 1, okay? If I hit 0 with identity, what do I get? 0, okay? So C naught, this gate here, says if the control qubit, this is the control qubit, is in the state 0, do nothing to the second qubit. If it's in the state 1, flip it, do a not, do an X on it. Yeah? Yes? But this qubit isn't a superposition of 0 and 1. Yes. I don't know what the difference between those two is. Yes. Sure. Yeah. Same thing. Okay? Because we hit it with the Hadamard first. So it's a mix of off and on at the same time. So what's its action on this? Well, we did it, but maybe I did it too fast. Hadamard is 1, 1, 1 minus 1, if I'm remembering correctly, and I think that was a 1 on root 2, was a number out the front. And so we're acting on the state, which is, I'm sorry. No, sorry, not Hadamard, C naught. C naught's a big matrix. The way to do it is what, let's go back and, this is the trouble. Like once you start doing big matrices, I need the Dirac notation, to see it. This is why we're doing this, right? Okay. So this is C naught, okay? It says, if I have a state 0 on qubit A, then I apply the identity to qubit B. If I have the state 1 on qubit A, then I apply X. Yeah? That's how to read that. And and in both cases, I leave the first qubit alone. Yeah? So now I'm going to consider a circuit which does. First, you'll have to read back to front. It's really confusing. But because matrix multiplication and circuits are written in different directions. First of all, I'm going to hit the first qubit with Hadamard, and do nothing to the second qubit, and then I'm going to do a C naught on the both together. So, I told you how to apply tensor product operators, as the first one applies to the first qubit and the other one applies to the second qubit. That gives us the plus state. We put this here. That's where we are right now. We're at this point in time. Now we hit it with C naught, which is this is an operation on 2 qubits, one that doesn't factorize. Okay, this is important. C naught doesn't factorize. It's this. Yeah? So we expand out the first one, which we know was in the plus state, using the distributive rule. I can write it like that. Okay, so C naught acting on, yeah, that step might have been tricky, but it's just algebra. Yeah, it's just distributive rule. So now I can apply this. I know how C naught acts. Remember, like, if I know how things act on basis states, then by linearity, I can extend their action to any state. Okay, if I know how an operation acts on every basis state, then I know how it acts on any state in the vector space by linearity. Okay, this is important. Okay, by just doing this trick, I just expand it out. Okay, in its basis. I spent all that time explaining how to express things in terms of basis states, right? So here, I know how C naught acts on this state by definition. Does nothing, right? Yep. I know how C naught acts on this state. It hits that with an X. Yeah? Again, the definition. That's how I define C naught to act. Yeah? Okay. So I just do that. I'm just going step by step at a time. You can see that it's acting with 1 over there, or the identity over there, and with X over there. X meaning not. And what I get out just from this, just from acting nothing on there and X on there, what I get out is this beautiful Bell state, right? So I've created entanglement by this combination of two gates. Okay, so that's a standard quantum circuit to do that. Yep, we good? Cool. And in fact, we can do this on lots of qubits at the same time. Okay? That means we can, that's actually just with the Hadamard. This is not entangled. This is just the Hadamards. This is just hitting a bunch of qubits with Hadamards. This state, where every qubit in a long chain of qubits is in the plus state, is actually if we interpret those as binary digits, that's a superposition of every number between 0 and 15, right? And so now you're thinking, well, shit, if I can represent with how many did I say? 4 qubits, I can simultaneously represent every number between 0 and 15. I could do computations, mathematics, and I can simulate classical computers with quantum computers, obviously, right? I can do computations on all numbers at the same time. There's a massive catch, because at the end of the computation, we need to do a measurement. And a measurement collapses the superposition, okay? And we're going to get one answer to one of those computations we did. So quantum computing sucks. Which means that quantum algorithms have to do incredibly clever and subtle things with these superpositions before we do the measurement and get the answer at the end out, okay? And it is being shown that in certain cases we can do such, clever things. Famously, you can use it to factorize large numbers more efficiently than classical computing. But factorizing large numbers has limited practical applications. Okay, I've got time. All right. Yes. I mean, it turns out to be super hard, okay? But there are times, yes, you can come up with clever things because there are clever things you can do. But like, go and look up. Like my hope at the end of this, let me get to the end of this, right? And then I'll show you the book to read if you want to find out about the quantum algorithms, which actually can take advantage of this stuff, okay? You have to do extremely clever and weird things, but it is possible to sometimes get stuff out, okay? But you know, we're still in like the taking baby steps with this at this point. Right? It really isn't there. So copying a bit is something we do millions, billions of times a day, right? We just assume that we can take an image on our hard drive and send it to my daughter, take a photo of one of these azulejo buildings and send it to my daughter in Barcelona, and she'll get a perfect copy of all the bits in this image. So this is a process. Copying is a process which takes a bit in arbitrary state and another bit and produces the bits in the same state, in the same state of the first one. Okay? All agreed that what copying, that is how we represent copying in our, of a classical bit in our formalism, yep. We ask, what's equivalent quantum gate operating on qubits? Right? It's got to take an arbitrary state of a qubit, an arbitrary state in the block sphere, and copy that to a second qubit, which started out in the default 0 state. Right? So we'll get two block spheres with the same vector on both of them. We're going to call it U because it has to be unitary. We know it has to be unitary. Now, let's start with how it acts on the states 0 and 1. So we have a gate which takes 0, 0 and gives me back 0, 0 and takes 1, 0 and gives me back 1, 1. Can we do this? Yeah, of course we can. This is classical copying of a bit. Of course we can do this, right? Quantum mechanics can do this. We know that. We do it all the time. But we also need it to take plus 0 and give plus plus. All right? So let's check that it does that. There's a little tensor product in there I didn't write in, of course. What did I use here? Oh, no, I haven't done it yet. Okay, so I've just expanded this out. Haven't done anything yet, okay? Now, how did U act on 0, 0? Well, we just said produces 0, 0. How did U act on 1, 0? But we also need that this equals plus plus. Right? So I'm computing the same value in two different ways. First, I used what we know about how this acts on these classical states, right? And now, I'm using the fact that this has to act on plus 0 to give me back plus plus. And the question is this state here, this state here? I think you can see that the state is that state going to be the same as this one? If I multiply this out, how many terms does it have? Four. This times this, plus this times this, plus this times this, plus this times this. This is right? That's not that state. This state's a Bell state. This state's a product state. There's no way that these are the same state. So is U plus 0 plus plus? No. There's no such matrix U which satisfies those properties we're looking for. And so it's impossible to perfectly copy a quantum state. Right? And this is entirely, I don't know, to me, I don't know, to you guys, is that intuitive? To me, it's entirely unintuitive that it should be impossible to copy the state of a qubit. Entirely surprising. It's called no cloning theorem, right? Very easy to prove, right? And yet seems to say something quite, I don't know whether deep is the right word, but something pretty basic about physics and information, right? On the other hand, it's possible to show that a quantum state may be transmitted perfectly from one place to another using classical communication if Alice and Bob share an entangled qubit at the start. But does that violate no cloning? No, because Alice destroys the state of her qubit in the process. This is called teleportation. The circuit is quite simple, right? So basically, this is a Bell state. These are the two halves of a Bell state, of an entangled state. Alice has a qubit and one half of the entangled state. Bob has the other half of the entangled state. Alice does a C0. Then she measures one of her half of the Bell state. She does a Hadamard, and she measures her original qubit. That process of measuring that qubit, her qubit, is what destroys it. Okay, it collapses its state into, up or down or whatever it is. What did she measure it on? I don't know. It doesn't say. Probably Z. She measures the other one, then she sends the two classical bits that come out of those two measurements to Bob, right? They're just 1 or 0, the classical bits. And then Bob does a C0. Oh no, it's not even really a C0, it's just a knot. It is a C0, but it's almost like a classical, I don't know, what do you call that? But controlled by a classical, it is a C0. And then does a controlled Z operation, which is similar. And perfectly gets out Alice's original state. This is actually quite unintuitive, folks, because the original qubit state is a position on a two-dimensional manifold. And these two classical bits are like 1 and 0. They have 4 possible states. Somehow, she sent, I mean, of course, you know, in practice you can never do this with perfect fidelity, but somehow she, you know, sent an infinite amount of information. It's not true, but by sending 2 classical bits, all right? Now, obviously, they had to start out by sharing an entangled Bell state. This is also pretty unintuitive, okay? Pretty surprising. But notice the thing about it. It doesn't violate no cloning because Alice had to destroy her qubit. Now, if you want to see how quantum teleportation works or anything else, yes.
How long does it take to go from one qubit to another? So my question is it fast enough that if we go back and forth, we essentially get both states in both places?
Like what if, how quickly could Bob send the state back to Alice? The thing is that they wouldn't be able to do anything with it, right? Because Bob presumably at the end wants to do some, you know, what is he going to do with this qubit, right? He wants to do something with it, ultimately to do some measurement, okay? Could he use it, could you create some fancy entanglement between some quantum computation that's running over there and something that's running over there? I guess so, right? Yeah, sure you can. Yeah, why not? I mean, they start out by sharing an E-bit, right? Yeah, I suppose so. My intuition is yes. I don't know. I haven't thought about it, but yeah, I mean, but ultimately, that kind of doesn't get you anything because ultimately, you know, the whole thing about all this stuff is at the end you're gonna measure something, right? And at that point you destroy it, right? So, you know, don't think that you can use this stuff to, at first people were concerned that this whole stuff of entanglement between, things separated by long distance could allow superluminal transmission of information and stuff like that. Superluminal means faster than light, if anybody doesn't know. And no, it can't be used to do that, okay? This is called teleportation. I don't know why, it's a stupid name. It just took, teleportation just means that I can take a state of 1 qubit, perfectly reproduce it in another place by transmission of 2 bits of classical information. Yeah, beyond that, I don't have many comments to make. If you want to know more, my goal with all of this was to get you guys to a point where you could sit down with this book, all right, and read about quantum circuits and quantum information. This is a very, very readable book. It's not the one I learned quantum information out of, but it's really good, and it's what most people use as their first textbook. Another really good, I have shamelessly borrowed the approach taken by this guy, John Watrous. It has an excellent series of videos on YouTube, which are maybe even he's going a little bit more slowly than I've been able to go. We take his overall approach I've stolen, shamelessly, okay? I've taken that approach of starting talking about classical probabilities and classical processes, and so that's a really good series of videos on YouTube. And we're not going to talk about density matrices. So those are great, and the other place to go is the Qiskit website, okay? So Qiskit they've done an amazing job of, compiling all sorts of information. It's really easy to get started writing little Python programs that build quantum circuits and do stuff, and they have lots of resources for how to do the best known quantum circuits. Thank you guys. I realize that was really long, and what are the which? That's an interesting question. Really, yeah, I know. You mean input in the sense of how to get some initial data into there? Yeah, well, yeah, okay. So we kind of assume that every qubit relaxes back to the 0 state at the start of the computation. So the initial state of a quantum circuit looks like this, okay? Now, if I want to, say that I want to represent the number 0, 1, 1, 0, 0, okay? Then what am I going to do? Well, I can just hit this with an X, hit this with an X, right? And then I've created that number in my circuit, okay? What are these gates really? They're little microwave pulses that rotate the state of the qubit. So you have a little controller there that's kind of telling the qubits what to do. Yeah. Yeah, that's something you would call a spin qubit. Spin qubit, that is not how actual existing quantum computers today work. Existing quantum computers work by superconducting circuits. Is there an easier way to explain what a charge qubit or a flux qubit is? There's not. I've been talking from the quantum information perspective, which is very abstract, and the closest analogy is to an electron spin. Okay, as I said, actual qubits are not that. They're a quantum 2-level system where you have the ground state at energy E, and you have, or let's call it 0, and you have an excited state at energy epsilon. Okay. And from our point of view, that's all we care about, right? Yeah. I can give you some references if you want to read about there's a very good book actually about actual superconducting circuits and qubits. Written by a Spanish guy. It's a really good book about it. I can give you a reference if you like. Any other questions before we? Yes. Yeah.
I played with it a little bit, but I know that program was cancelled, and I know there's another one, but can you still play with it?
100%. Yeah. 100%. You can. Yeah. You can still go, and you can. I mean, some of their smaller devices are still available on the cloud for use for free, right? Yeah. But they're building. Yeah, no, but it's still about the same. Yeah, the free ones are that, but they're now making, Heron, I forget how many, 400, 800, or something like that. I forget. Yeah, but they're building devices with hundreds of qubits now, limited connectivity and stuff. But you can still absolutely go there and play online with. But also it's just fun to just play with the simulator. Yeah. Yes. That's yeah. Qiskit is their. Sorry, I didn't explain what Qiskit is. Qiskit is a framework, I guess. I don't know for building quantum circuits. You can then run the quantum circuit locally on your machine on a simulator. Okay, which what is as I said, it probably just builds a bunch of matrices and applies those matrices to the states. Okay. Or you can actually run it, or you can then go and actually run it on their devices, which are available on the cloud, and they have some simple devices there with just a few qubits. Or if you want to pay money, I'm sure you could run it on some of the. Mm.
According to my understanding, there is a quantum chip available up to 1,000 bits.
1,000 qubits?
Yes, 1,000.
Yeah, that's about the order of magnitude. I didn't check. I should have checked. I don't want the latest Heron device. I'm not going to say anything which might be wrong, but it's that kind of order of magnitude. Yes.
I want to ask for a suggestion.
Yeah.
To you, on what extent
look, so far, the issue today is that the coherence times are extremely small. So these devices are like subject to all kind of interference from the environment that is dephasing the, so the devices lose coherence after a very short time and everything goes to shit, right? We're currently in this NISQ era, right? We don't have enough qubits to be able to do error correction, but we're getting there, okay? There are experiments going on right now to do error correction on qubits, and I think my personal prediction is that this part of the problem will be solved quicker than people expect. And once we have error correction on the, look, I mean, I'm talking completely 100% outside of what I should be talking about. This is hardware. I don't know anything about this. But once we have that error correction, right, then you should be able to do longer computations, right? And once that becomes, then you'd be able to run stuff like Shor's algorithm. Currently, Shor's algorithm, as I understand it, cannot be run, but just because the decoherence times are too short. You need. I'm not going to say. I'm not going to speak beyond my knowledge, but we need bigger devices, and so that you can do error correction, which means essentially building things in terms of logical qubits, where you have multiple qubits representing the state of one qubit, which lets you correct errors. Right? You have redundancy there. Yeah. Guys, I would love to get a photo of everybody together, if you all wouldn't mind. That would be awesome. Okay. If you want to come up to the front or something, I don't know. Yeah. Yeah. Good. Thank you, guys. I hope.